Hello everyone. We are going to see how statistics can be used for environmental science. But then basically what is statistics? That we need to learn first. So this is an introduction to statistics. Now why do we need statistics? So there are two main reasons for which we need statistics. First of them is to capture the diversity and then how to interpret things. So we'll see these with illustrations, and then later on we'll study what are some basic statistics. Okay, what are the quantities that can be computed from the data which will be available to us. So this is a brief outline of the talk. First we'll see the need of statistics, and then we'll compute a few things from the given data. So let's start. Now this is the formula that most of us know. Area of a circle is pi r square. Wherever we go, it doesn't change. So if someone gives you radius, you can uniquely decide its area. Similarly, speed of light. Wherever I go, speed of light is going to be 3 into 10 raised to 8 meter per second. It doesn't differ from person to person, or it doesn't differ from source of light, and so on. Same thing about water. Molecular formula for water is H2O. It's a fixed thing. You don't need to worry about that. Everywhere it would be H2O. There will be 2 hydrogen and 1 oxygen. But what about if someone asks you, what is the length of an earth worm? Now what is length of an earth worm? Can you give me one specific answer? No, it can be say very small, say 2-3 centimeters. It can be very large, say 10 centimeters, and so on. I cannot give one specific answer. Then how do I distinguish between an earthworm and a snake? How large thing will be a snake? How small thing will be an earthworm? And so on. So we need to have something which captures the variation of lengths in the earthworm, and still at the same time it gives some defining criterion. So that's where statistics comes into picture. So let's go into this problem of lengths of an earthworm. So suppose I want to study earthworms, what would I do? I would try to collect a few earthworms and measure their lengths. So basically what I would do is I'll take actual measurements. Collect an earthworm, measure its length, record it, and that will be my data. Now the thing is, how many earthworms can I collect? There are infinitely many earthworms in the earth. Suppose I decide to see the neighborhoods in the surroundings of my house. If I want to collect, still there will be thousands of earthworms. So how many can I collect? There has to be some limitation. So though my population of earthworms is infinite, I can have a small sample from that. So what we have is a sample. So what I can do is, I'll collect say 100 earthworms, and I'll say okay, now it's enough. On the basis of these 100 earthworms, I'll collect some data and decide to study what happens. Okay. So population was my entire thing, whatever is there in the universe. So like however earthworms are there, but my sample is a finite thing. It's a very small thing. So that I have a sample. Now I collected data on some earthworms and I plotted a graph. So this graph looks like this. Now what I can observe is, in my sample, the smallest length observed is 4 centimeter and the largest length observed is 16 centimeter. So it means that in my sample also I had a big variation. I had small earthworms which were having length 4 to 5 centimeter and big earthworms having length 15 or 16 centimeters. And then how many are there? If you see in the graph, at the center there is a peak. Means most of the earthworms are between say 8 to 12 centimeters. Few are below 8, few are above 12. Okay. So from this graph I can see some pattern. And this pattern is going to further help me to decide what is the general length of an earthworm. Okay. So this kind of graph is known as histogram. And it's the basic thing which we draw when we have some data in hand, to see how this data looks like, what is the spread of this data. Okay. Now let's compute some values actually. So in this, minimum was 4.819 centimeter. Then maximum was 15.179 centimeter. And average length is 10.055. Now why do I need average length? See, 4 centimeter thing is also an earthworm, 15 centimeter thing is also an earthworm. So is there anything which is a general criteria which can say, okay, normally earthworms are of this length. So I need to have something. Same thing about humans. Suppose I record heights of human beings. Most of them would be between 4.5 feet to say 6.5 feet. Very few would be below 4.5 feet. Very few would be above 6.5 feet. So normally we say like 5 to 6 is a normal range. So such kind of ranges can be computed using statistics. Next example is for acid rain in Norway. Okay. So here the object was to study the precipitation if there is any acid precipitation, if there is any acid rain. Most of the time we keep on hearing stories about pollution and all. So if there is a pollution, then we know that there is an acid rain and so on. So I need to measure the amounts of acids in my rainwater and decide whether there is actually a pollution. So some Norwegian scientists did this study, and their period of study was 1974 to 1978. So they had data on these years, and there were small lakes, and they recorded measurements of acids in those lakes. The data on which, the variables on which the data were recorded are this. pH of the water was computed, then sulfate concentration, nitrate concentration and calcium concentration. Now what do we expect? That if there is an acid rain, then concentration of these things should increase. If there is a sulfuric acid in the rain, then sulfate should increase in the water. So let's plot the graph. This is graph of one of the variables. Now you can see on x-axis I have a time scale. So as my time, like as I go away, there is a slight increase in the y quantity. Okay. So this is the graph of sulfate concentration. So the sulfate concentration is slightly increasing. So what do I mean by slight increase? Is it a really significant increase, or I can safely ignore it? Do I need to be serious about this pollution or not? That I need to decide. Now some of you may feel that no, this is not significant. But those who are very much cautious about environment, they may say that no, this is also a significant thing because this is how things worsen slowly and gradually. Let's compare with other data. Suppose this red line is in some other area and black is our original thing. Now what is the thing? Now this red thing is surely increasing. It's a drastic increase. Whereas this black is, compared to red, it seems to be a stable thing. Then there can be something in between. Now this blue line, if I compare with red line, then I'll say blue line is not much increasing. Whereas if I compare with black line, then it seems to be increasing. So which comparison is more appropriate? What is more accurate? So for this, we need to have statistics. How much change is a significant change? Okay, for example, there are some tablets which guarantee that height will increase. Height for children will increase faster. So how much increase in height is significant? That we need to decide. So that level, that threshold can be provided using statistics. So this is second objective of statistics. So first objective is to summarize variation into some general number, and second objective is to see what is significant, what is non-significant and so on. So the basic problem is there any evidence of abrupt change in the values of the variables, pH or sulfate or nitrate and so on. So this is our basic objective, and if there is any change, then in such cases we need to study what is the change. Is that change increasing or decreasing? If suppose sulfate concentrations are decreasing, then obviously it won't support my claim that there is an acid rain. So I need to record the quantity of the change as well as the direction of the change. Both the things we need to record, and then we need to study. So next thing is, we were studying 4 things. So independently also we'll study, but at the same time they can be related. So we have to study correlations between them. So next major question would be, are there any evident correlations among these 4 variables? Then second correlation can be due to geography. If 2 lakes are closer to each other, then water in one lake is going to be similar to the water in another lake. So due to regional similarities there can be some correlation. And third thing can be due to time. Data recorded in 1 year and data recorded in say last year, first year and last year, they will be obviously very different, but data recorded in first year and second year, they would be more or less similar. So correlation can enter by 3 ways. First is due to the variables, then due to regional similarities, and then due to time scale. So that also we need to study. So is this correlation significant? This thing also we need to study. So for that also we have some measures in statistics. Now let's go to those measures of statistics which are going to help us to conclude about these things. So first is known as measures of central tendency. Now what do I mean by measures of central tendency? Central tendency means it's the thing which can measure what is normal, what is general. It's like simple average. Most of us compute average marks when we get scores in some exam. So average marks give me an idea of how I have performed in all the subjects. It is some single number which represents my performance in all the subjects. So that average is one example of measure of central tendency. So the first basic measure of central tendency is the mean. So this mean is a simple average. Okay, that we have always been studying in schools. This is the simple average. Second measure of central tendency is median. Now sometimes it may happen that I am not interested in the average value, rather I am interested in middle located value. So location wise, which is the middle thing. For example, I have say 5 people and I want to pick up one person who is having average height. Now if I compute actual heights, then there may not be even one person whose height matches that average height. That number might be still different. Whereas if I arrange those persons in the ascending order of their heights, I can pick up the third person. I have 5 people, so third person would be like having medium height kind of thing. So in such situations, we have what is known as median. And then there is one more thing, which is mode. Mode is again a measure of central tendency. And what is mode? Mode is the most common observation. For example, we go to market for buying shoes. So how do shoe companies decide which sizes to manufacture? Because if you measure accurately, then every person will have some different measurements, but still most of us fit in the normal ranges. So that is the mode. They compute which size can fit maximum number of people, so that size is generally manufactured. So mode is something which is most common observation. So these are the 3 basic measures of central tendency which can help us to decide what is the general, normal or typical content in the entire data. But then, okay, let's have some example for that. Here we have a bacteria data. So the data says that it's known that in some water sources in a given city, bacteria are present. And we need to study what is the amount of bacteria present. Okay. So there are say 30 water sources. We took a sample of size 5 from each of the water sources. So what did we do? We took 5 test tubes and then went to one water source, filled up those 5 test tubes with 1 centimeter cube water from that water source, and we repeated similar thing for 30 water sources. So from say each lake, suppose we have 30 lakes, from each lake we have 5 test tubes, and then we kept those test tubes in the lab, and after some time we observed if there is any bacteria growth in those test tubes. So this is the histogram of that. So you can see on x-axis I have only 5 things because I had only 5 test tubes for each water source. So for one, frequency means y value is 5. So what does it mean? It means that out of the 30 lakes, there were 5 lakes where only 1 test tube showed bacteria growth. From each lake we had 5 test tubes, but then these 5 lakes were probably less polluted, so only 1 test tube showed bacteria growth. Whereas if I see for x equal to 5, means last bar in this histogram, then the frequency is 7. Means there were, out of these 30 legs, there were 7 legs for those, all the test tubes showed bacteria growth. All the 5 test tubes for these 7 sources showed some bacteria growth. So what I can conclude is, these 7 lakes are more polluted because all the water samples from those lakes turned out to be having bacteria. Whereas those lakes which showed bacteria growth in only one test tube, first 5 lakes, they are less polluted relatively. Then we can represent same data in the tabular form. So this is the frequency table. Same graph has been translated into tabular form. So number 1 has frequency 5, 2 has 8 and so on. And my capital N is the total number of sources, so it is 30. So in all there were 30 sources. And now if I compute mean of this data, mean everyone can compute. So this mean is 3.03, simple average. Then median. How do I compute median? Now I know 1 is repeated 5 times, 2 is repeated 8 times and so on. I have 30 observations. So my median would be basically something between 15th and 16th observation. So here, you can see here, my 15th and 16th, both the observation would be 3. If I arrange the data in the ascending order, I have first 5 1s, then 8 2s, and then 5 3s. So my 15th as well as 16th observation would be 3. So my median is 3. And next is mode. Mode we saw is the most common observation. So here you can see frequency of 2 is largest. Okay, 2 is repeated 8 times. So frequency of 2 is largest, so 2 is mode. Sorry. Now, sometimes it may not be enough to know about mean. Okay. For example, there are 2 students. One student got 70 marks in 3 subjects. In all the subjects, he got 70 marks. Whereas another student got 70 marks in one subject, 40 marks in another subject and 100 marks in third subject. Now for me, I'm sorry. Now mean for both of them would be 70. But then we need to decide which student is better. Because this student has got only, second student has got only 40 marks in one subject. Still his average score are 70. So we need something known as measure of dispersion. So dispersion means spread. How the values are spread around the mean. So there are 3 major measures of dispersion. We'll study them one by one. First is range. So range is simple. Maximum observation minus minimum observation. So in this data, maximum observation is 5, minimum observation is 1. So the range is 5 minus 1, so it is 4. Okay, so range is 4. Next is the thing which is known as interquartile range. Now what do I mean by interquartile range? Now interquartile range is computed using something known as quartile. Now what is quartile? Quartile is a point which represents a kind of 1/4 division of the data. So if I want to divide my entire data into 4 parts, I need 3 points. First point at the end of 25%, second point at the end of 50%, and third point at the end of 75%. So if I draw 3 points, Q1 which is 25% point of my data, Q2 is 50% part of my data, and Q3 is at the 75% of my data, then these Q1, Q2, Q3 divide my entire data into 4 parts. So interquartile range is the difference between Q3 and Q1. So this means that my 50% of the data is between this interquartile range, Q1 and Q3. Because before Q1, I have 25% data. After Q3, I have 25% data. So between Q1 and Q3, I have almost 50% of the data. So we have interquartile range. For this data, it turned out to be 2.25. And then there is third measure of variation, which is known as standard deviation. Standard deviation is square root of squared deviation from the mean. We know that observations are distributed around the mean. So what we do is, we take the difference of each observation from the mean, compute its square, and then take sum over all such observations and divide by total number of observations. This thing is known as variance, and square root of that is known as standard deviation. Now why do we take square? Why don't we simply take differences? Because the thing is, my differences will be positive and negative. So they may cancel out and I may get a feeling that the deviation is 0. Whereas actually, I'll have two opposite deviations which are cancelling. So to avoid such confusion, we need to have squared deviation. So this is how standard deviation is computed. Once we compute these means and variances and so on, next thing is to see how the graph of the data looks like. We first saw histogram of earthworm. Similarly, here is some graph for another data. Now what is the peculiarity of this graph is, most of the large bars are to the left and to the right I have very small bars. And if you see the range, then on the right side I have very small bars but up to very high value. Most of the large things end before 2, but still I have small things even after 7. So this is known as the data is having a long tail on the right side and left part is a big. So mode is towards 0. Mode is towards left. So in such cases, we say that my data are positively skewed. So positively skewed data has mode on the left hand side and it has a long right tail. Now such kind of data are useful for say modeling incomes and so on. Most of the people will be having very low income and like very rich people will be very few in number. But there will be still many of, like the numbers will be huge. Their income can be in say billions and so on. But that number of people having that income will be very less. So for such kind of distribution, we can use positively skewed distributions. Now exactly opposite of this is the negatively skewed thing. So this is just a reflection. So here you have a longer tail on the left hand side and on the right hand side we have a mode. So this is known as negatively skewed data. So when we get some data, we first plot histogram of the data and then decide which statistical model can be used. Each statistical model can be used only for some particular type of data. So either for positively skewed data, negatively skewed data, or something known as symmetric data. Now what is symmetric data? If like in that earthworm histogram, in the center we had a peak and on both the sides we had small tails. Neither the right tail nor the left tail were like very long. So that was the symmetric data. So basically there are three types of data: positively skewed data, negatively skewed data and symmetric data. So once we get some data set, we'll plot its histogram and then accordingly decide which statistical model can be used. And then just like the horizontal spread, we have to think about vertical spread. So on the basis of vertical spread, there are again three types. The one which is having a very high height and slender thing is known as leptokurtic. This vertical thing is measured through something known as kurtosis. So if the kurtosis is high, then it means that the height is very high whereas spread is comparatively low. So that red thing is known as leptokurtic curve. One which is normal means almost understandable, reasonable height and reasonable spread, that is mesokurtic. And third thing is platykurtic. Platykurtic is having shorter height and it is a bit flattened thing. So on the basis of skewness, we can categorize data into three parts, and similarly on the basis of kurtosis, we can categorize data into 3 parts. So these are the basic things that we can observe from the given data. So once we get the data, we would plot its histogram to decide whether it is symmetric, positively skewed or negatively skewed, and then we can compare it with the normal curve, normal distribution, which we'll be learning in the next lectures. So that normal distribution is mesokurtic, so it is in between. So we can compare it with the normal curve and decide whether the given data is leptokurtic, platykurtic or mesokurtic, and then we can compute mean and variance, median, mode, means whatever measures of central tendency and measures of dispersion that we have learnt. So those we can compute and get a basic idea about the spread of the data and how does the data look like. So these are some summary measures which can summarize our huge data into some pictures and some few numbers. So I think today I'll stop here. These are some of the references that can be used for studying such things. Thank you.